Hello, my name is Max Rudolph, and I am a first-year master's student at Georgia Tech. I will be presenting our paper on range-limited coverage control using air-ground multi-robot teams. This work is motivated by the use of multi-robot teams in tasks such as autonomous farming, surveillance, and search and rescue. For example, a field of crops can be autonomously monitored by a team of robots surveying moisture content in the crops or crop ripeness. For these tasks, we often want to perform coverage control in which the robots aim to distribute themselves so that the environment is observed optimally, paying attention to important regions and disregarding less important regions. Traditionally, coverage control using a team of ideal and identical robots has been solved by an algorithm called Lloyd's algorithm, proposed by Cortez in 2004. However, in recent years, there have been several works applying coverage control to teams of heterogeneous and non-ideal robots. This means that robots within the team have range-limited or anisotropic sensing capabilities. Performing coverage with these teams cause issues because if a robot cannot see beyond its sensing range, it won't explore, or if a team is comprised of robots of differing capability, a robot that can see very far might be assigned to a region of little interest. In this toy example, you can see that if the robot were limited to sensing what was inside of its red circle, it would never explore the bright, important region to the right. In this work, we answer the question, how can we best leverage the sensing capabilities of an autonomous robot team comprised of aerial robots with coarse but broad sensing capabilities and ground robots with fine but range-limited sensing capabilities? In the original Lloyd's algorithm proposed by Cortez, N robots follow the spatial gradient of the cost function defined on the left, where Pi is the position of robot I, V of Pi is the ith Voronoi cell created using the robot locations as seeds, and phi of Q is the environmental density or importance function. Using the multi-robot farming example from earlier, the density function can be thought of as the ripeness of the crop in a given region of the farm. Naturally, if robots are harvesting, they would want to be closer to the ripe crop. So, the cost function is weighted such that the robots are penalized the farther they are from the harvestable regions. Note, in this work we assume the density function is normalized to a probability density function. On the right is the controller derived from the spatial gradient of the cost function, where C of Pi is the mass center of the ith Voronoi cell, and kappa is a positive constant controller gain. Here, we see a group of 5 robots surveying a non-uniform domain, with the density function mapped to the brightness of the gray background. In this example, bright regions could denote where the harvestable crop is, and dark could represent where unripe crop is. Because we are assuming ideal sensors, each robot can sense its entire Voronoi cell, and can thus accurately calculate where the mass center is. Note, in the final configuration of robots, each robot converges to the mass center of its Voronoi cell, denoted by the crosshairs. Again, note that a robot's controller depends on being able to sense its entire Voronoi cell, because it looks for the mass center of that Voronoi cell, circled in red. Next, we will show that when a robot cannot see its entire Voronoi cell, undesired behavior arises. In this example, we are assuming that the robots have range-limited sensing capabilities, and thus cannot see outside of their red circles. Clearly, you can see that the robots do not explore the region on the right, and only observe the region on the left, which they can sense. This is more similar to what happens when these algorithms are deployed on real systems, because it is likely that the real robots have sensing capabilities that are limited in one respect or another. Now I will discuss our heterogeneous team formulation. We have 2 types of robots: ground robots with range-limited but fine sensing capabilities, denoted by the orange animations, and aerial robots with relatively broad but coarse sensing capabilities, denoted by the blue dots. The Voronoi partitions are slightly different than in traditional coverage control. The aerial robots form Voronoi partitions which are in thick black lines, and then the ground robots form Voronoi partitions within the aerial partition, as shown with the thin black lines. In order to generally distribute robots to regions of interest, we assign a regional importance value, or weight, to each aerial Voronoi cell that we call sigma. This sigma is the difference between the proportion of robots within an aerial cell and the proportion of robots that should be in an aerial cell. Using the farm example, if there is a region with a lot of ripe crop, ideally we would want a lot of robots there. This ideal proportion of ground robots is found by using the aerial robots to coarsely integrate the importance function in their respective Voronoi cells. Again, the aerial robots are able to do this because they have broad but coarse sensing ability. On a farm, this could be a drone with a camera that measures how green a region is. Not a perfect measure of ripeness, but it's close. With this regional importance weight, sigma, we can say that aerial cells with a negative weight are in need of more robots, aerial cells with a weight of 0 have the correct amount of robots, and cells with a positive weight have a more than necessary amount of robots. For use in a controller, we are concerned with pushing robots in cells with too many robots into cells with not enough robots. So, we want a measure of whether a ground robot should stay in its aerial Voronoi cell or leave. We can start to do this by lower bounding the regional weight sigma by 0. We define sigma j hat as the maximum between sigma j and 0. Now we can use these regional weights sigma and sigma hat to build a controller that balances the local Lloyd controller with the globally distributional controller. Intuitively, when sigma hat is near 0, meaning that a particular region has the appropriate amount of robots, this controller will be dominated by the local Lloyd controller. When sigma hat is near 1, meaning that a particular region has too many robots, this proposed controller disregards the local Lloyd controller, and the term on the right, which points towards the region most in need of robots, will dominate. Again, the local controller is the same as the spatial gradient introduced earlier. This proposed controller switches between allowing robots to globally and locally explore regions on the domain, and thus effectively uses the aerial information to overcome the range-limited sensing of the ground robots. In this proposed expression, A min represents the mass center of the aerial Voronoi cell with the lowest cell weight sigma, not the bounded sigma hat. Because we implement this algorithm on a discrete system of robots, we encounter discretization problems when the regional weights are very close to 0. So we often round them to 0 once they get within a small range. As sigma approaches 0, however, our proposed controller converges to the range-limited version of Lloyd's algorithm. This does not pose a problem because the robots are already near the regions of interest and thus use their local sensing to make fine adjustments to their positions. Here, we can see the proposed controller in action with 4 aerial robots and 10 ground robots. Notice that the algorithm has distributed 6 robots to the larger region of interest and just 4 to the smaller region of interest. Here, we show the computed cost of traditional Lloyd's algorithm in red, range-limited Lloyd's algorithm in yellow, and our proposed algorithm in blue. We can see that the computed costs between the proposed algorithm and traditional Lloyd's algorithm is similar, and both outperform the range-limited algorithm. It is important to note that just because traditional Lloyd's algorithm and our proposed algorithm have similar converged costs does not mean that the final configuration of the robots in both algorithms will be the same. Finally, our contributions are as follows. We propose a method to leverage the sensing capabilities of aerial and ground robots in order to observe an a priori unknown domain. We develop a way to encode robot distributional efficiency in our regional weight, sigma. And we can achieve a similar coverage cost using a team of non-ideal heterogeneous team of robots using our algorithm when compared to an ideal team of homogeneous robots using traditional Lloyd's algorithm. Thank you for your time.